Hello, I'm Sarah Heisinger with the University of Pittsburgh Chemistry Department, and today we're going to drop the bomb and determine the resonance energy of benzene. The goal of this experiment is to determine the resonance energy of benzene experimentally and theoretically. The experimental value was found using a bomb calorimeter to measure the heat of combustion of CDDT and cyclohexane. The conditions of the bomb calorimeter was excess oxygen in constant volume. The measured heat of combustion was then used along with the vaporization enthalpies to find the resonance energy of benzene. Theoretically, benzene resonance energy was determined through the use of the computer program SciGRESS. SciGRESS calculated the heat of formation of CDDT, cyclohexane, and benzene. This experiment is important because resonance energy is the extra stability conjugated systems have. Understanding resonance energy allows for the understanding of aromatic compound behaviors and chemical reactions. In addition, the method of bomb calorimetry to determine heat of combustion can be used in future experiments. In everyday life, heat of combustion is specifically important in the production of engines, and everyone knows how important engines are to help with transportation. So next we will move on to my hypotheses. The first hypothesis is that the change of internal energy of combustion of CDDT will be greater than that of cyclohexane. This is predicted because the reaction is isodesmic. The heat of combustion is related to the change of internal energy of combustion through the equation delta H equals delta U plus RT delta N, where delta N is the change in moles of gas, delta U is the change in internal energy, and delta H is the change in, or is the heat of combustion. Therefore, it is predicted that CDDT internal energy of combustion is larger than that of cyclohexane due to the isodesmic reaction relationship. The second hypothesis is that the temperature change for CDDT will be greater than that of cyclohexane. In this experiment, which is run at constant volume, the change of internal energy of combustion is equal to heat. So delta U is equal to Q, which equals heat capacity times the change in temperature. Since the heat capacity is a constant, the change in temperature is what's guiding the heat. And because it is hypothesized that the change in internal energy is greater for CDDT, it is also predicted that the temperature change for CDDT is larger. Next is finding this theory of the theoretical resonance energy. The reaction between benzene and cyclohexane to create CDDT is isodesmic. An isodesmic reaction means that the number and type of bonds in the product is equal to the sum of the number and type of bonds in the reactants. As you can see, CDDT has 3 double bonds and 9 single bonds. Cyclohexane has 6 single bonds. Benzene has 3 double bonds and 3 single bonds. If you add up all the single bonds, 3 plus 6 equals 9. And if you add up the double bonds, 3 plus 0 is 3. Therefore, it is expected that the heat of formation of the products is the sum of the heat of formation of the reactants, but this isn't the case because benzene has resonance. Therefore, the difference between CDDT heat of formation and the sum of the reactants heat of formation is the resonance energy. So below is the mathematical equation which shows this, where N is the number of moles and delta HF is the heat of formation. Now moving on to the procedure of finding the theoretical resonance energy. First, the molecules were drawn to SciGRESS. For cyclohexane and benzene, an optimized geometry experiment at the PM6 level was performed. For CDDT, however, another step had to be taken in order to find the lowest energy conformation of CDDT at room temperature, and then the heat of formation of the experiment was performed at the chemical sample PM6 at current energy. For the experimental determination of resonance energy, the complete Hess's law cycle is shown. Each step corresponds with either heat of vaporization value or heat of combustion value. Literature values for cyclohexane and benzene heat of vaporization and benzene heat of combustion will be used. CDDT heat of vaporization and CDDT and cyclohexane heat of combustions will be experimentally measured. In order to find CDDT heat of vaporization, a set of data that follows the temperature dependence of vapor pressure was used. Using the data, the natural log of pressure was plotted against inverse temperature. The regression line is in the form natural log of pressure equals negative heat of vaporization over R, which is the gas constant, times inverse temperature plus a constant. So if we draw it out, here is our regression line, y equals mx plus b. Therefore, by multiplying the slope by the negative gas constant R, enthalpy of vaporization of CDDT is found. The definition of heat of combustion is the change of internal energy of combustion plus the change in the number of moles times RT, where R is the gas constant and T is the temperature. Under constant volume conditions, which is used in bomb calorimetry, the change in internal energy of combustion is equal to the heat of the reaction, which is Q. Q is equal to negative C bomb times delta T, where C bomb is the heat capacity of the calorimeter and T is temperature. Because the initial and final temperatures are not stable, a correction equation for delta T is utilized. 5 points are used along the temperature versus time graph. Point A is the time of firing the bomb. Point B is time of 60% of the total temperature change. Point C is the time of maximum temperature. Point I is the time of initial temperature, and point F is the time of final temperature. R1 in the equation is the slope between points A and I, which is the time of firing the bomb and time of initial temperature. R2 is the slope between points C and F, which is the time of maximum temperature and time of final temperature. Below is a diagram of the calorimeter setup, and you can pause the video to read over the experimental procedure. Using the Seigras method described previously, the theoretical heat of formation of benzene, cyclohexane, and CDDT were obtained. Seigras reported the heat of formations in kilocal per mole, so the conversion from kilocal to kilojoule was performed, and it was found that the value of the benzene resonance energy was 201.3927 kilojoules per mole. As discussed earlier, the natural log of pressure was plotted against inverse temperature. The regression line was found to have a slope of negative 5,733.9. Since the slope is equal to negative the heat of vaporization over R, the value was multiplied by the gas constant and the sign was changed. Therefore, the CDDT heat of vaporization was found to be 47.672 kilojoules per mole. The cyclohexane heat of combustion calculation was broken down into 5 steps. First, the change in temperature was found. Second, the total heat was calculated using the delta T in step 1. Next, the heat caused by the wire, unburned wire, and gel capsule was calculated and are represented as QW, QWU, and QGel respectively. These components were then subtracted from the total heat to obtain the heat caused only by the cyclohexane. Lastly, the heat of combustion was solved in step 5 and was found to be negative 4,261.842 kilojoules per mole for trial 1. The CDDT heat of combustion was found using the same steps as the previous slide. However, in step number 3, the CDDT experiments did not use a gel capsule, so only the heat of the burned and unburned wire was calculated and subtracted from the total heat. After all the calculations, the heat of combustion for CDDT of trial 1 was found to be negative 7,278.256 kilojoules per mole. Here's the summary of the results. The heat of combustion values for cyclohexane and CDDT are averaged between the two trials. The percent error was calculated to compare the experimental and theoretical value of the resonance energy, and it had a value of 6.85%. In conclusion, the goal of using bomb calorimetry and Seigras computations to find benzene resonance energy was successful. However, the percent error of 6.85% shows the experiment was not perfect. One source of error could be the instrument accuracy. For example, the temperature probe only reads to 0.001 degrees Celsius, the scale only read to 0.0001 grams, and the ruler only read to 0.1 centimeters. Therefore, each measurement has a certain amount of error. Another limitation could have arose from measuring the unburned wire. Measuring the unburned wire was difficult as some pieces were not the original thickness and some were hard to make straight due to them being very small. This could have led to inaccurate heat calculations causing too much or too little heat due to the wire to be subtracted away from the total heat. Regarding the hypotheses, the first hypothesis was supported. The magnitude of the delta U combustion of CDDT was larger than cyclohexanes as shown back on slides 10 and 11. The second hypothesis was not supported. It was found that the temperature change for CDDT was smaller as seen also in the trial 1 results data. To correctly analyze this hypothesis in the future, both CDDT and cyclohexane would need to use a gel capsule. The temperature change had 2 differing variables between samples, the type of fuel and whether or not the gel capsule was involved. Here are some improvements to better the results. The first is to use the same calorimeter for both samples. The precision would be improved because all the samples are under the exact same conditions. The level of accuracy between 2 calorimeters can be different, leading to less precise values. Another improvement would be to run more trials. The average values was used in the final calculation of resonance energy. With more trials, the precision of the data would improve. Lastly, a transfer pipette could be used close to the volumetric flash line when measuring the water. By using a transfer pipette, a more accurate amount of water will be used. The exact amount of water is important because it is used in determining the total heat of the reaction. If too much water is used, the change in temperature could be smaller than the true value. There are other techniques to determine benzene resonance energy. The first is to measure the heat of combustion of cyclooctatetraene. COT is a benzene ring with one extra ethylene within the ring. Therefore, it is unconjugated and non-aromatic. By comparing the COT heat of combustion minus one ethylene part with the benzene heat of combustion, benzene resonance energy can be obtained. This method may be less accurate than the method used here because it assumes COT heat of combustion can be equally split between the four ethylene groups. Another method would be to use benzene heat of hydrogenation. Benzene resonance energy is the difference between the calculated and experimental heat of hydrogenation. This method may be more accurate than the method used here because only benzene is considered in their calculations. Bomb calorimetry also has other applications. It can be used to determine the calorie content of food. This can help nutritionists improve the quality of food on the market. In addition, it can be used to determine the most efficient biofuel. This can help the world move towards renewable energies, improving the environment. In conclusion, bomb calorimetry is a useful tool and has many applications. Thanks for watching.